Assalamu alaikum students. Today we are going to discuss the Benzyne mechanism of the nucleophilic aromatic substitution. Benzyne mechanism is an elimination-addition reaction or elimination-addition mechanism. Substitution by hydroxide and bromobenzene can occur but only under the most vigorous conditions, such as when bromobenzene and sodium hydroxide are melted together at very high temperature, like this one. But in the presence of ammonia and sodium amide, the reaction can occur very easily. The amine can be replaced, the amine can be added to the benzene ring. A similar reaction with the very powerful reagent of NaNH2, which supplies the NH2 ion, also happens, but at rather lower temperature. Then the question arises, why? If we look benzyne, the structure of benzyne was studied when it was trapped at 6 degree Kelvin. That is minus 257 degrees centigrade. And it was found that it has a triple bond. The triple bond is about 1.26 angstrom longer and weaker than that in the ethine, which is 1.20 angstrom. And the adjacent carbon-carbon bond is about 1.39 angstrom. That is slightly shorter than that in the benzene. Here, these are the bond length. This one, 1.38 angstrom. It is slightly shorter than the carbon-carbon bond in the benzene, which is 1.39 angstrom, and slightly longer than the triple bond in the ethine, which is 1.20 angstrom. Here. So this bond is longer than the actual triple bond of the ethine, and this bond is shorter than the actual carbon-carbon bond in the benzene. Nucleophilic aromatic substitution at very low temperature. The chloro group is mildly or moderately electron withdrawing. Traditional SNAR reaction require heat. The traditional reaction, the nucleophilic substitution of the aromatic compounds, required heat. But this reaction, this is only at minus 30 degrees centigrade. So now the question is, does this also go through the addition-elimination mechanism? An addition-elimination mechanism here doesn't seem right, considering that the nucleophilic aromatic substitution reactions with far stronger electron withdrawing groups like nitro, which is more stronger than chloride, require higher temperature and longer reaction times. Another observation was that no reaction occurred under these conditions when the R2 position were attached to alkyl groups. So a hydrogen is necessary at one of these positions for the reaction to proceed. Now these observations, like here, this compound, it has no hydrogen available at the R2 position. Both the R2 positions are occupied. So no reactions occur without R2 hydrogens. Now the second observation. A second observation was that in case of below, only the R2 and meta products formed and never the para. Here, this is chloride, this is removed, and we get two products. One is R2, this one, and the second one is meta, this one. But this para product is not possible, is not obtained, never formed. These were quite complicated problems, and it was solved by Robert in 1953, and he published his research in 1953. What he does, he used labeled carbon-14. He synthesized chlorobenzene in which the carbon to which the chlorine was attached was labeled with C14. Chlorobenzene was synthesized that contained C14 carbon at the carbon attached to the leaving group, chloride. Now, what is the hypothesis? If the reaction goes through addition-elimination, the product with NH2 bonded should be exclusively to the C14 labeled carbon. The product should be here, like this one. But the observation was not like this. In fact, the reaction produced a mixture of two products in about 1:1 ratio. The actual observation was that he got two products. In one where the NH2 was attached to the label carbon, and in the second when NH2 was attached to the adjacent carbon. And both the product were in nearly 1:1 ratio. The NH2 was not on the carbon to which the leaving group was attached. So how can this result be explained? These results are not consistent with the addition-elimination mechanism. Step 1. Elimination to form the triple bond. He explained this like in this way, that first is the elimination. NH2 abstracts the hydrogen, and then a triple bond is formed. It's called benzyne. Now, either side of the triple bond can be attacked by the nucleophile, explaining the equal mixture of the products A and B. Now the nucleophile can attack either this carbon or this carbon of the triple bond. And so both the products can be obtained in equal amounts. Path A, ammonia can attack this one, and we get the product A. Or the ammonia can attack the adjacent carbon to the labeled one or the other side of the triple bond, and we get the product B. So this is not an addition-elimination reaction, but is an elimination-addition reaction. Like here, the para-bromotoluene, we will get para-toluidine and metatoluidine in 50%, 50-50 or 1-1 ratio. Reactant in halobenzene with no electron withdrawing groups on the ring. There are no electron withdrawing groups on the ring. And a strong base is used, like sodium amide. So now the Benzyne mechanism. The amide first extract the proton from the benzene ring, and then this empty orbital, these electrons attack the bond and the bromine is removed. Loss of bromide occurs and we get a benzyne. The sodium amide extracts a proton. The benzyne intermediate forms when the bromide is expelled and the electrons on the sp2 orbital adjacent to it overlap with the empty sp2 orbital of the carbon that lost the bromide. So these two sp2 overlap with each other and form the triple bond. Benzynes are very much reactive species due to the high strain of the triple bond. The triple bond produces a high strain in the ring, and that's the reason that benzynes are quite reactive. Now, nucleophilic substitution on the benzyne intermediate. The sodium amide or the amide will now attack the benzene from at either side of the triple bond. It attacks here, and then this group will abstract the hydrogen and we get the para-toluidine, or it will attack this carbon of the triple bond, the other end, and we get the metatoluidine. Now we will come to the reactions of substituted benzynes or arines. The substituted benzynes can produce multiple products. Here, the unsymmetrical arine can be attacked at A or B, and from attack on A we get the product ortho product, and from attack at B we get the meta product. The reduced selectivity. Since the aromatic pi system is at right angles to the triple bond, what's not relevant is the ability to donate a lone pair to the ring, like OCH3 methoxy, or accept a lone pair from it, like nitro. However, inductive effects are still relevant. That is, the electron withdrawing effects that occur through single bonds. Why? Addition to the triple bonds create a negative charge on the carbon, and electron withdrawing group stabilizes these negative charge. The closer, the better. The closer the electron withdrawing group, the better it will stabilize the negative charge. So a key principle in the addition of nucleophile to arine is that addition tends to happen so as to place the negative charge closer to electron withdrawing substituent. The addition will occur in such a manner that the negative charge should be closer to the electron withdrawing substituent. When the triple bond is between the meta and para carbons, attack will favor the para product, since the negative charge ends up on the meta carbon closer than the para. When the triple bond is between the ortho and meta carbons, attack will favor the meta product, since the negative charge ends up on the ortho carbon closer than meta. Look at here. When an electron withdrawing group is present, the intermediates where the negative charge is closest to them will be favored. This one. This is an arine. Here is the electron withdrawing group. When we have an attack on the para position, so the negative charge is closer to the electron withdrawing group, and that is favored. But from meta attack, the negative charge is further from the electron withdrawing group, and this is disfavored. Similarly, if the triple bond is ortho and meta carbons, then the attack on meta, because here the negative charge is near to the electron withdrawing group, so the meta attack will be favored, and the ortho attack will not be favored one, because the negative charge is further from the electron withdrawing groups. So the presence of electron withdrawing groups will also direct the attack of the nucleophile, and the resultant negative charge, when it is closer to, how much it is closer to the electron withdrawing group, that product will be more favored. Thank you very much. Thanks for your patience. Thank you.